Our afternoon session on demand dispatch and microgrids, and we have pleasure to listen to Jean-Yves Le Boudec, co-professor at EPFL and also IEEE fellow, and also Jean-Yves has interest in performance and architecture of communication systems and power grids, and he has He has received numerous awards, such as best papers at Infocom and ACM Signatories Conference, and also Bennett Award in Communication Sciences. So,
thank you very much. Thank you, Anna. So the work I will be presenting today is a joint work with Professor Mario Paolone's lab in electrical engineering, and I'm in computer science and the communication systems department at EPFL, and this is the work of a group of PhD students and postdocs that are listed here. I will first describe a system, so some engineering. This system is about controlling a grid. We call it a microgrid because this is probably where most of the applications we think will be, but this is quite generic and could apply to any grid, typically a distribution grid. And then this raises a number of theoretical problems, and I'll dive into one of them in the second part of the talk. Here is a small typical example of a situation where a system would apply. Assume we have a microgrid, and a typical example in Switzerland, for example, is when a residential building owner wants to install charging station in the parking lot or the basement of the building. As soon as you have more than 2-3 cars, the power supply of the building is not sufficient. So you have limitation on the grid side. So a classical solution is to, if you can't afford to do grid reinforcement, is to complement by local power generation, perhaps local storage if you don't have vehicle to grid, and then to optimally use all the resources that are in the building and in the charging station. So one way to see what we would like to do is we have a 1 megawatt power limitation here. We would like to charge the cars by as much as possible while not enforcing this maximum power rating here, but while also opportunistically optimizing every slack that we have. The slack can come from the fact that there is power generation due to PVs, but also due to the variations in the load usage. So we have to be fairly fast because the dynamics of PVs, for example, in the order of seconds. So we want to control the microgrid to utilize it optimally while respecting its constraints. And as we will see, what we're able to do as an interesting side effect is to enable dispatchable feeder or feeder a microgrid or an entire distribution grid in the neighborhood that can provide ancillary services to the main grid. Therefore, that can participate in the stability of the main grid. How we can do that is by having a cyber system. So we implement microcontrollers, small Linux computers, embedded computers, one that is in charge of the entire microgrid, and one logical instance that is in charge of every large resource that we are controlling. The large resources are, for example, the charging station, one controller for the charging station. If we have a large thermal load, we have also one controller for these big thermal loads, for example, a cooler in an air conditioning system. And in our case here, we also have a stationary grid battery. Building such a system, I mean, there are various ways to do it. I mean, it's an optimization problem. If the number of variables is not very large, we can simply do it by traditional MPC or even simple optimization methods. But what seems to be important to us is to do it in a very simple way. So the software has to be robust, and robustness of the global system is a key issue. So in order to achieve that, what we believe is the success for such complex systems is to have reusable building blocks that do fairly simple functions. The main intelligence of such a system is the grid agent, so the software here that instructs the power set points of the different devices, And we make it simple by defining an abstraction between the resource agents, that are the controllers that are close to the resources that are being used, batteries, charging station. The protocol between, so we define a protocol between the resource agent and the grid agent, which we call the COMELEC protocol. And this protocol makes all the abstraction on the resource agent. So the job of the resource agent is to export to the grid agent a very simplified and abstract description of what happens here. This description contains the capabilities, the power set points that this resource can implement, active and reactive power, because we are controlling an AC grid, and also not just the power set point that it can implement, that's what we call the PQ profile, also virtual cost function that will be used by the grid agent to do its optimization. So this virtual cost is not necessarily a monetary cost function. It is a function that will be used to transform the control into optimization. And cost, for example, for a battery might depend on its trajectory, intended trajectory, and its state of energy. For example, if a battery is used simply for compensating forecasting and dispatch plan errors, the goal of this battery is to be as close as possible to its midpoint, state of energy 0.5. Then it will have a cost function that is a function of how far it is from this midpoint. If it's fairly much charged, like state of energy equals 0.7, it will have a cost such that consuming energy is very expensive, but producing energy has a negative price. So it wants to be discharged because it wants to get back to 0.5. Other scenarios can be found if the battery is used to displace energy, for example, from the middle of the day to the evening. Then we do, in advance of the real-time execution, we do a dispatch plan that will dispatch the battery such that it has to be full or as full as possible towards the end of the afternoon. So that will be reflected in the cost function. So what we see is that the battery story and the dispatch plan are not visible to the grid agent. The grid agent will simply, which acts in real time. The goal of the grid agent is to be the real-time operating system of this microgrid. This one will simply react to costs and derivatives that are prices here. As I will explain in a second, we also need to export the uncertainty about the operation of those devices, and that leads to very interesting problems and makes this system unique, I believe. So once the grid agent has received all this information, it simply instructs all the resources about active and reactive power set points that hopefully are inside the domain of feasibility that has been advertised here. So, so we do control of a microgrid by controlling the injections, which also is an indirect control that poses a number of technical difficulties. A few words about the uncertainty. The uncertainty is captured by what we call the belief function. So the belief function that is exported by a device controller, the resource agent of a controller, has the job of quantifying what is, with overwhelming probability, a set in which this device will operate when it is instructed to do something. So if this device, for example here, a PV plant that is controllable, the only thing you can control on the PV is to curtail it, so we can dynamically curtail it. If you instruct it to do P set, Q set, it will do something that will perhaps not be P set, Q set. It will be in a function, in a set here that depends on what you instruct it to do. For example, here, if the operating point is here, and what we do with PV agents is ultra short-term forecast. It is possible at the time scale at which we operate, of 1 second or sub-second, to do a forecast which is better than simply 0 Pmax of the power, the DC power that a PV will receive. We can do it simply by data analytics of the inverter, and that gives already fairly good forecasts, or we do it also with all-sky cameras and pyranometers that can even do very accurate forecasts, because at the time scale where we are, we can lose all the 60% of the power within a second, but this is typically because a cloud is coming, and this cloud we will see it a bit before. So we can have forecasts. For example, assume the forecast here is, this is the PQ plane of what the PV is doing, so assume the operating point is here, but the forecast is that there could be a drop, not to zero, but up to this. Then if this PV agent is instructed by the grid controller to do this point, the belief is this one, so the uncertainty associated with this target set point is given here. If, in contrast, it is instructed to do this here, it will be able to do it exactly because it is in the minimum of the range that we believe is given by nature. It can even do less, but there's no reason to do less than what it is instructed if it is instructed to do this one. So this quantifies the uncertainties due to nature in the case of PV, but also, and many other resources, but also the inaccuracy of the model we have. So when we model, for example, a battery, we find there's always a fraction of a percent of inaccuracy in what we read from the different instruments and what is really happening in the battery. So all the devices do this. They export to the grid agent the possible set points that they can implement and their uncertainty, and then the grid agent simply at every time step, so every tenth of a millisecond, which is the nominal frequency we use, it will simply minimize this function. This function is what? The xi are the set points, so x is a shorthand notation for PQ, the active and reactive power of controlled resource I. Here, this is the cost, the virtual cost that was exported and is time dependent, but we drop the time dependency here. So this is from the latest advertisement known by the grid agent, plus a penalty term that accounts for the feasibility of the grid. So this Z, by doing a load flow derived from the xi, gives us the line currents, the voltage magnitudes, and we want them to be within the bounds here. And a third term is about the interaction between this microgrid and the main grid. So x0 is the active and reactive power exchanged at the point of common coupling. So we can control the amount of power that is exchanged if we are doing, for example, a dispatch grid. If we have a dispatch plan for this grid, then we have already promised or subscribed to a given power consumption. We can also participate in voltage control, for example, by receiving instruction from the main grid about the reactive power that needs to be injected or consumed here. So the job of the grid agent is simply in the sense that it is now a completely abstract mathematical problem. All the quantities it sees have nothing to do with a battery or a charging station or a thermal load or a cooler or anything. It is simply a completely abstract problem. But it still needs to make sure that what we call admissibility holds. Admissibility is the fact that if the grid agent instructs all the resources to do xi here, they will not necessarily do xi, they will do something that is in the advertised belief functions that correspond to what was the set point. So we say that a collection of set point is admissible if for any practical implementation that's in the uncertainty bounds, the implemented value satisfies the security constraints, which are voltage magnitude and line current constraints here. So this is implemented in several microgrids. The first one we have is in this building on the EPFL campus. This is Mario Paolone's lab. So we reproduced here one of the Sigre low voltage microgrid with solar PVs on the roof and on the facade that are controllable, a battery, Le Clancher battery here, a thermal load emulation, which is a flex house representing a building with 8 different rooms. And this is, so the software, which was a prototype until middle of last year, is being made industrial and hopefully commercialized by a startup company that is given here and was created by some of the students who worked on that. Here are some results of measurements taken on this microgrid here. Here we're showing the dispatch plan. So we have dispatched this grid, for example, by saying during this time interval it is energy neutral. Many people often speak of an energy neutral building as something that consumes as much as it delivers, as it produces. But here we mean a strictly energy neutral, so the power exchange at the point of common coupling is zero. We assume for whatever reason, through the bidding process that was discussed in the previous talks, for example, the microgrid operator has decided to run at this point, and here a bit later it wants to consume more, so negative here means consumption. And here we're showing in blue what is actually implemented by our system, which differs from what is actually the dispatch plan. First, there is always some small variability that we cannot prevent, but here there is some intended variability that comes from providing frequency support. Here we provide support to the main grid, so we measure the frequency, and 50 hertz in our country is the nominal value. We see here the frequency is higher, therefore this grid should consume more, which is what we see here. It's consuming more, and here the frequency is lower and the grid is producing a bit. So we have an example here of a microgrid, but this we think of it as a grid in a building, but it could be a grid in a neighborhood that behaves more like something that can be abstracted more easily by global system operators. Because now if we go to Swiss grid with this dispatch plan, then we first participate in the global stability by providing frequency support. So here this is implemented by having the grid agent emulate a droop control. And then based on that, in the utility function that the cost function that it minimizes, it will provide this result here. That can also be used to provide revenues to this microgrid system, because if Swiss grid or other TSOs provide adequate tariffing schemes for such services. Here we see this grid has one line, the line that goes to the PC to the main grid, that is concentrating all the power, and we see that the job and has this 30 amps power limit. And so we see that the job of this system is to maintain the current within the limits here. So and we see that it is close to the limit. Now it's inevitable that there are some uncertainties because our system is in discrete time. So every 100 millisecond we react to whatever has happened. So during the 100 millisecond there is this uncertainty, which is captured by the belief set, but has to be factored in. So this is what the grid agent does. The grid agent has computed set points such that this margin is acceptable. In independent research, we have asked the question, what happens if we have now a country where instead of having microgrids that are like today, they are open bars in some sense. We connect to the main grid, we receive voltage stability from that. Perhaps we receive very little, we do very little payment because the microgrid does not have a lot of power flow exchange. So if we have this free riders, microgrids here, which is the state today with very little generation, but if we assume we have a lot of generation, then there is a well-known side effect, which is the cost, the impact on reserves. So the system operator, the global system operators, needs to compensate for all the variability that exists in the distributed generation by putting some reserves. So this is well known, and some grids have easy access to data. So we use the Western Denmark grid to evaluate this. So we looked at what is the amount of reserve that needs to be put in place if we have a traditional way of operation. So all the microgrids are operating without any contract, without any dispatch. And if we want an expected load non-shed of, for example, here 10 to the minus 3 or 2 to the 10 minus 3, we need a certain amount of reserves here. Now we can do the same exercise by taking into account the fact that there would be a number of penetration of a number of local grids that are dispatched because they have a real-time operating system like the one that I've shown here. Of course, the dispatch plan is never implemented exactly. So we took statistics on, because our grid has been operating for over a year, so we took statistics on how well we followed the dispatch plan, and we assumed the other grids would do similarly. And based on that, we can compute the same amount of reserve that is needed, the amount of regulating power that is needed to achieve a certain quality of service measured by expected load non-served here. And that allows us to find that, of course, as expected, we need much, depending on the penetration of the number of dispatchable feeders, the amount of reserve is highly reduced. We can even equate the storage either in the form of batteries or demand response systems that are deployed in the total in this interconnection versus the amount of reserve capacity that can be saved if we have this storage. So if we have, for example, this operating point here, if we use this grade of service for 4,000 megawatt hour of storage distributed in throughout the continental Denmark, this is equivalent to having half a gigawatt of reserve here. I will very quickly mention just a few ancillary aspects that are not the focus of this week, but perhaps of other weeks. Since we do control by computers, we have to put a lot of effort on making them reliable, or as reliable as the non-computerized systems. We use for that duplication almost everywhere. We duplicate the network here. We use IP multicast to also simplify the control of the network. And we use various mechanisms to make sure that nasty side effects that occur when we use replication of the controllers don't appear. So we replicate the main controllers, the grid agent in particular, also the large battery agents. We do active replication, not backup, but we have constantly 2 grid agents that are computing hopefully the same set points. And if it's not hopefully, there is a lightweight consensus, which we call quartz, that has been developed that has a guaranteed latency and make sure that the active replication would not lead to split brain syndrome here. We also take security seriously, so all the protocols are authenticated and encrypted, and encryption authentication is fairly simple at the IP level with IPsec, and we worked also on authenticating the multicast sources, which is a bit more tricky, but can be done here. So all of this is available on GitHub. So it's a Linux implementation of the API and of the resource agents. The grid agent is we still keep it proprietary, but all the API, if you want to write your own grid agent or if you want to interact with our grid agents, you can do it here, and you can also develop resource agents. So this is the system I wanted to share with you. Here now I will dive on one of the many interesting problems that this system caused us to tackle, to address. The very first problems we had to address is how to do everything very fast. For example, we do load flows, so we had to develop iterative methods that are able to compute the load flows as fast as is possible today. So, but I will not talk about that. I will talk about a more subtle problem that has to do with some of the questions that were asked this morning, which is when we do an OPF, we say, okay, here are the optimal power set points we should have everywhere. But how do we know whether the grid is implementing the operational points that correspond to that? Because from the power set points to the state of the grid, we have an inverse problem with possibly many solutions. So in that sense, how can we control a microgrid by playing only with the power set points, right? It seems impossible because we should control the state, the electrical state of the grid. But we know we can't physically control the state of the grid except with extremely complex systems like power switches or whatever. In particular, this shows up during the grid agent jobs, which is what we call the admissibility test. So the grid agent, when it's doing its projection, when it's doing the, we optimize by doing simply gradient descent, so because we do it very fast, so we don't need to find the optimal point, because in the next 100 millisecond the optimization problem will have changed. So we do simply a gradient descent, but it's not so simple because we need to project it onto the set of admissible set points. I will not talk of the projection problem today, but I'll talk just about the test, the admissibility test, given a set point S. So that's a collection of power injections, active and reactive power, of all the resources, and I'm asking the question, is it safe? Is it safe given that I'm not sure the grid will do S, the grid will do something that I can quantify, because all the resource agents have quantified their uncertainty, so I know I will be in some set capital S. And the question is, am I sure that if all the power set points, the only thing I know is where we are now, and where the injections will be, bounds for where the injections will be, am I sure that all the currents and the voltage magnitudes will be okay? That's the admissibility test. So to talk about it, I need to first establish some terminology and some notation. So we call V the electrical state, so that's the complex phasors. So we measure and all the buses of the grids with PMUs, we measure the electrical state. So these are the complex voltage phasors that completely describe the electrical state. From this we can derive all the voltage magnitudes, obviously, but also all the line currents and the power flows on all the lines. And we have the space that we control, which is in fact the set of power injections, active and reactive power. We have three-phase, typically unbalanced microgrids, because for those small grids the balance is not guaranteed. So we are in those space here. We call F the power flow mapping that maps the electrical state to the power injections, assuming there is one single slack bus with a node voltage. And the load flow, so F is a quadratic, well-known quadratic function. The inverse problem is known as the load flow, finding S, given S, find a V, right? But we know that's a nasty problem. It has no solution if the S is unfeasible, which in principle you could never get into, but the grid agent might instruct a collection of devices to do things that are unfeasible, in which case we will never get there. But if it instructs things that are implementable, there might be many ways to go there. Right? So are we sure that the way we will go there will satisfy the security constraints in particular? And we also want to have what is sometimes called static voltage stability, that we are not at a singular point of this power flow mapping here. So how do we, given this terminology, we can cast the admissibility problem that the grid agent has to solve as follows. We know the electrical state of the grid because we observe the grid. So V0 is the set of all the complex voltage phasors at all the buses of our grid. This is essential. If we don't have that, it's impossible to know on which electrical state trajectory we will be. Given that we think S will be in some uncertainty set capital S, given also that at the beginning we are at this set, so the initial condition is in this set, can we be sure that the resulting states will satisfy the security constraint? So that's all we know. We put no assumptions on the dynamics, so we don't have a dynamic time domain representation of the grid, because we don't want to do that. We don't want that the grid agent needs to have a model of the inverter at the sub-millisecond time scale and all that stuff. So we don't know that. We don't need that. We don't want to have that. But what we require, of course, is that the resource agent that is sitting on the inverter has properly accounted all the local peculiarities of its controller through the quantification of this uncertainty set here. So one concept we introduce here to simplify the notation is what we call a domain of V control. So we say that a set in the power injection space is a domain of V control, where V is a subset of the electrical state, if the following is true. For any continuous trajectory of the electrical state that is starting at V0 such that the corresponding power injection is in the set S, if we know that at any time, so F is the power flow mapping, so if we know that at any time the power injections are in the state S, then it must be that the electrical state is in the set V. Of course, we need some assumption here. I'm assuming that the trajectory, V as a function of t, is continuous in t. It's the only assumption we're making. If it's not continuous, of course, it could jump any time to any other multiple solutions. So that's a reasonable model of our microgrid. It will not jump except if there is an explosion or a catastrophe somewhere. It will not jump, so the trajectory is typically continuous. But there are multiple solutions. So we know, for example, we've done a load flow here. We know all solutions in S are, for any S in the state S, there is a load flow solution in V, but are we certain that the true trajectory will stay on this solution or will it exit? Right? That's the question that we're asking. There are multiple ways to address it. In this talk, I will go through one part of theory, which is perhaps the simplest we can do here. First, let's look at the things that don't work. Obviously, for S to be a domain of V control, we need that any value that is in this set has a load flow solution that is in V. If that doesn't exist, then it's impossible. So it's necessary, but it's not sufficient. Here is an example that is taken from this paper by Nguyen and Turitsin of 4 years ago. Here I'm showing on the right is the S space. So we're here only in dimension 4. So I'm showing the projections at one bus, and at the other bus here I'm showing the possible active and reactive power. And I'm showing here the electrical state, which is also in dimension 4, and at bus 1 and bus 2 here in blue. We see that if we start from this point here, so the first thing we see is that if the set that we have is this blue line, in practice it is never such a thin line, it's usually sets that don't have zero Lebesgue mass, but this is just to make the point here. For any value of S that is in this product of two lines, there is a solution which is in the feasible set. The feasible set are the sets such that the voltage magnitude is plus or minus 10% of the nominal value. So we have to be between those two curves here. So there is always a solution here, but the point is there is also another solution that goes outside. So it is true here that for any value of the power injections, there is a load flow solution. If I start from this point here, I'm not guaranteed at all. In fact, if we do a simulation and follow the trajectory by continuity, if we start from we start from the same power injection, but if the original electrical state is here, we will stay within the domain, but if it is at this point here, at the diamond, it will exit. Although the diamond is inside the domain, it will take the other branch here. So which branch will the electrical state take? It's very hard to say. Here we see only two branches, but in reality, even in a small grid with two nodes like here, we're already in dimension 6, and then there's not two branches, but a countable, but large number of branches. So we could say, well, let's impose a stricter thing. Let's impose that for any power injections, we are in a smaller set here. We restrict the set of voltage states, of electrical states, such that there is one and only one solution here. So there is a unique solution here. Well, this is not sufficient, at least this alone is not sufficient. So by taking the same example here, so it's the same example, I'm just zooming on a part that we had before, and here I'm showing the electrical state, an electrical state space A and B, and if I take as V the union of the two, there is always a unique solution for any point here, but when we reach this boundary point, the electrical state should to remain without VA union VB, it would need to jump from one branch to the other, which of course the system will not do. So if I move from here, I will not stay in the union of the two. I will of course get out of the system. So it's not sufficient that I have found criterions through optimizations or feasibility of linear programs if I approximate all of this by linear local things. It's not sufficient to be able to say there is a unique solution inside a voltage a complex electrical state here. But almost. With a little more work, we can see that by adding a simple topological information, the answer is yes. If the state, the set V and the set S are such that there is a unique load flow solution for S in V, and if both are open in the usual topological sense, they are defined, for example, by strict continuous inequalities, then yes, then it works. Of course, the examples I gave before, the sets were not open, and this could not work. This is this seems like almost obvious. It looks like the inverse function theorem, but it is not, right? The inverse function theorem is saying the opposite. The inverse function theorem says if we have a non-singular point, there is a domain around where those things will be a one-to-one mapping. But the problem here, I'm not asking a local question. I have a given S. I want to say, is there a global one-to-one mapping? And am I guaranteed not only that there's a global one-to-one mapping, but that we will not escape that through any continuous trajectory. So it's a different result. And this result requires, is true in fact for any system of the same kind, provided that the function f is quadratic. So we exploit here the quadratic nature of the function f for this result to hold.
Jean-Yves?
Yes?
Are these sets V and S, can you quantify their size, or they're just local neighborhoods?
No, this is if V is open, S is open, and if there is a unique load flow solution in V for every S in S, then it's a domain of V control, whatever the size of V and S. That's a theorem. It has nothing to do with the size. Now, as I will discuss a bit later, finding for some S, finding a V that satisfies that is typically very hard if S is very large. Right. And I'll say a few words about that. We also need another result which is related to that, which is we talked about existence of solution and not escaping here. Another result that we have is uniqueness. So the mapping from V to S is one-to-one. In other words, in a certain V, there cannot be two different load flow solutions that are there cannot be two load flow solutions in the same V, which means V is small enough, in fact, is isolated from singular points. Then we have that if that happens, then every V must be non-singular. So the intuitive thing is that it should be true, but this is true, and we will use this result. In the counter examples I gave before, there was a singular point, and the system was not a domain of uniqueness. So those results are always related. So given those preliminary results, we can transform the grid agent's admissibility problem into the following problem. So I'm giving a set which I call S uncertain here. That's the belief set that is given by the advertisements of our system. I know what is the current state of the grid. Then, in order to solve my problem, I need to find a set of electrical states such that it is open, it satisfies security constraints, it is a domain of uniqueness, and such that every injection that is in my uncertainty set has a load flow solution in them. And if you think about it, by applying all the results I gave before, because V is a domain of uniqueness, it will be non-singular. Therefore, by the inverse function theorem, S will be open. So I apply my previous result to S. So S will be a domain of V control. And since S contains S uncertain is contained in S, S uncertain itself is obviously a domain of V control. So this is our job. It is one of the methods we can use for this admissibility test. So the problem is to construct for a given set, this is given, find a set V, so it's a construction problem, such that we have uniqueness and existence of a load flow solution in S. So that is the problem we have to solve. And we have a solution for that. There are several papers have provided such solution. This is we believe the most general one. So in this paper we found a result of this kind that says, so again we are given initial conditions, V, V0, V hat and S hat. So this is a state of the grid that we have observed, and we know what are the power injections correspond to that, and we want to analyze whether a certain set around this one will guarantee that whether we can find a set V, such that all of those S, the red S that are in this set, have a unique load flow solution in V here. And the V that we will construct must be open here. And the condition is yes, it's possible by testing this condition. So we define a Xi, which is a norm, and a quantity, rho double dagger of V hat, which are given by ugly expressions that all depend only on the Y matrix of the grid. So they are static quantities that we can compute once and for all, at least as long as there's no reconnections and switches, but they are quantities that at our time scale are easy to compute. So once so if this condition is true, so this is a condition on S hat and V hat are given, they are the initial condition. So for all S that are not too far from this S hat, there is a unique solution in a nice, perfect disk around this initial condition. The radius of the disk is given by that here. So that allows us to construct a V, which is this disk here, which is of course open, and such that S is a domain of V control here. It's a bit more complicated. We need also to make sure that this V satisfies the security conditions. So there are additional constraints you need to test on the couple V hat S hat, and if that happens, that will ensure that this all the solutions in this disk are satisfying the voltage, magnitude, and ampacity constraints here. As Florian mentioned, this will typically work if the domain where we are is not too large, right? But not too small. We don't need to be too small either. This is what we found, at least on microgrids. Of course, perhaps on a meshed network that have hundreds of thousands of nodes, this would be another story. But here we're really targeting microgrids with three-phase, so the complexity is more on the three-phase side with shunt elements, so the complexity is really in modeling the microgrid itself rather than the size of the system. So here is an example for this relatively small network, where this is showing what is the uncertainty set for three of the phases here. So those are the numbers of the buses in this test networks, and those are possible uncertainty sets. We took them fairly arbitrarily, but just this is to indicate that our method is completely independent of the form and the nature of the uncertainty set. If we try on this set, the methods will not work in the sense that we will not find, here the sets are a bit too large, we'll find that the condition does not apply, but we can patch it by breaking the set into smaller pieces, which is what we do. This is our set here. So the problem is due to the third phase of this bus here. So we break the uncertainty set into 4 uncertainty sets with some heuristic that we have developed. And then we test separately each of the 4, because if each of those subsets is a domain of V control, then the collection also is. Because we know if we remain in this set here, we will remain, if the injections remain in this set, then the electrical state will remain in the intended set. So we break this and then we test each of those, and in this case, when the domain becomes small enough, then it works. So we can find and construct a patch now of a number of sets. Now, patching local solutions together does not necessarily give you a global solution, right? Otherwise, the complex logarithm would not have multiple branches. So we have that kind of problem. So this still requires some additional constraints that are given in this theorem here for the patching to be consistent here. We evaluated this on a number of feeders. For example, here we took one of them and added an uncertainty, which is taking the benchmark value and multiplying by a scaling factor that gives us the uncertainty set here. And we find that the set is in fact not large in the sense of our method, and we find that for whatever it is a domain of V control, we can find a set V that is secure and for which it is a domain of V control, which means for values of kappa that are 15% larger than the nominal value. And when we exceed this value, we need multiple partitions, but then we come very close to the voltage limits, which means that the method starts to having complexity problems when we are operating in a region where, in fact, we don't want to be operating here. Similar results hold for this feeder. We find also here the limits that we find are current limits when the method starts having problems here. Voila, I think I'm doing well with time. I'm not. So I hope to have made the case that it is possible with today's technologies to think of having distribution networks and microgrids that are controllable entities. So this is perhaps an alternative that we could factor in our reasoning about demand response or schemes to have a collaboration between the different actors. Here we're not talking of aggregators or of individual users or consumers that react to a global energy imbalance. We're talking of an entire distribution network that can be viewed from the global system viewpoint as a controllable resource with, of course, some constraints, but those constraints, we can quantify them as we do if we own a dam, a water dam, or a hydro plant, or a PV farm, or whatever. We're able to do that for a distribution feeder. We believe that it's possible to do it in a way such that the reliability will be similar to the reliability of the hardware that we have today when we have batteries and transformers and the like. And now in terms of theory, I believe that beyond the classical dynamical system stability and theory issues, there are also a number of problems that are more similar to what some people have studied in non-linear system theory, but where we don't have differential mappings or maps or inclusions of the kind, but simply we have simpler problems, but that have very important consequences to the control of such grids. Voilà. Thank you.
Yes, thank you. Very, very interesting. So what happens if there is some switching in the system? So you have to stop everything and to restart, or there is some kind of nervousness?
No, that's a very good point. In fact, we are deploying this also in the grid of a big Asian city, where they have they constantly do that. They change the topology of the grid very, very frequently. Although it's a distribution network, it remains single slack, but it's changing very often. But the timescale where we do it is only a software problem. So I mentioned that there's a startup that is commercializing the software. That's one of the things that they have done, is to make dynamic changes to we need to change the Y matrix, essentially. All the control is based on the Y matrix specification. So you need to change it, but it's purely a software problem because our system is memoryless, right? We obtain advertisement. We really have a grid operating system that instructs the power set point based on the static information of the grid and what the resources have advertised. If you change the static information, the optimization problem becomes different, but it's just a change of data in the optimization problem. It is stateless at the time scale of this system. Of course, there is always, you need to complement this with a dispatch plan. You need to compute and do a robust dispatch plan ahead of time to make sure that the power set points that the PCC receives are implementable with the resources.
So you need more than PMU. You need something on the status of the breakers in real time and synchronized.
We need an interface to know the state of the grid, correct? But we have that. Yeah.
And the synchronization, do you have some synchronization issues, or
yes,
how much you are depending on GPS? And and some.
This is all synchronized, where we receive GPS and then we distribute it with PTP and the White Rabbit system.
So you have synchronized topology and measurement. So you are
Yes,
both
yes,
sure
yeah.
that the topology is
Yeah, but for the PMU measurements, we have hard synchronization requirements everywhere.
But for the status of the breakers, sometimes.
Yes, yes, yeah. We have something I haven't described here. One of the things that we have done is the islanding maneuver, non-intentional islanding maneuver, and de-islanding. So when the circuit breaker, when a breaker is open or closed, and we need then within a fraction of a millisecond, we need to receive this information. This is where all the replication solutions I've shown were motivated. In fact, this was this example that motivated to do active replication of everything, because most of the time if we miss 1 or 2 or 3 or even 10 measurements, nothing very serious will happen. It will not be optimal, but if you're not optimal during 1 second, nobody cares. But there are time instances where you have to, when you're close to an operational limit, or when some topology change happens exactly. So we have also, I mean, it's very easy to imagine, once you have a system like this, it's very easy to do something that we have done also, which is to, when we become islanded, to elect a slack and change the slack depending on its state of energy, for example. So when we island, we typically take supercapacitors as slack, because they will be able to absorb the huge transients, and but they will very quickly deplete, and then we can change the slack, because the grid agent has all this information through the protocol.
Yes, I have the impression that your, let's say, your security constraints that you impose are conservative, and that when you scale the system, it may well be that, let's say, the range that you want to cover with your conditions becomes so big that you are not able to solve the problem, because then you have to divide.
Yeah, so I've shown here the system with a single level. So we don't, with such a system, we don't control with one grid agent a network with 20,000 nodes. So we control a microgrid or a local feeder. And then we have a mechanism to export to a higher level, typically a higher voltage level, another grid agent, to which, because it's very easy with this system, because we are able to model everything. So we know, for example, we know all the uncertainties. There are tricky things like doing Minkowski sums of PQ profiles, of uncertainty sets, and all that stuff, but we do linear approximations of all that. Then you can export, you can view an entire grid like a big controllable resource that has its own set of feasible PQs, single point, and also a given cost attached to it, which is the optimal cost that it would compute for all of its resources. So that's, we lose a bit of optimality because we need to do approximations at all in order to make that tractable. If there would be no approximation, it would be the same, but then it becomes tractable. We have, so what I've shown here is the microgrid, which is a low voltage, 1000 volts. We are then working on deploying it on the campus level, where we have the entire campus, and then every building is one microgrid, and then we have a medium voltage grid agent that is seeing a number of low voltage grid agents, which for it are resource agents. At least at 2 levels we know how to do it. I'm not claiming we could run continental Europe with that, but certainly we can run a fairly large distribution network with this technology.
Is it possible to include in the framework ancillary services, such as the grid agent should provide not just a constant power or voltage, but some voltage support?
Exactly. Well, that's what I've shown here for frequency support. We do that. I haven't shown it, but we do also voltage support.
How do you do that? Do you include this in the cost function, or?
Well, there is a higher level grid agent or somebody that gives us some information. For frequency support, it's very easy because frequency comes for free. If you need more, you need a higher level grid agent that, for example, it's a typical problem for the medium voltage grid agent, not on our campus because the grid is very stiff and we have no voltage problem, but on other grids, so with Romand Energy, we have this problem where they have a voltage problem, And then the grid agent of the medium voltage grid computes the optimal reactive power it needs to have, and then it instructs the local grids of providing this reactive power. I mean, all those grids are inverter-based. They can provide whatever reactive power you want for free, practically free. So they do it also. We have not done it, but you can very easily also provide secondary. Swiss grid follows secondary signals by simply modulating the dispatch plan with that. So that's the same method applies here.